Lionel Parreaux from EPFL. Our paper is on unifying analytic and statically-typed quasiquotes. Right, so let's start from some terminology. Everyone knows what a quasiquote is. It's a bunch of characters between quotation marks that represents free-form text. Now, quasiquotation is when you leave holes in such quotations, and these holes are to be filled in later. So, for example, here, X is a hole, and when we substitute it with words, we get an equivalent result as a quotation above. Quasiquotation is usually available in programming languages. Here's the syntax in Scala, where we use a $sign to mean an unquote, so it's to denote holes. So this is the same thing in Scala. And what we're interested in here is code quasiquotation, where we don't quote text, but we quote code fragments. So here's an example where we make a Lisp code fragment, Lisp construction, with 3 elements, and then we insert it in a bigger program. So we started by noticing that there's 2 flavors of code quasiquotes in the wild. So for example, there's the first flavor is analytic quasiquotes, where they were pioneered by Lisp. The point is that they treat code as data and they allow you to construct code and deconstruct code pretty much freely. But since metaprogramming is hard, they often result in runtime errors. So for example, if you have this piece of code, it's wrong to try to evaluate it with the run method because it's ill-typed. True is not an integer, and X is not even bound anywhere. So we're going to get an unbound variable error. And the other flavor of quasiquotes is the statically typed flavor. An example, the typical language for this is MetaOCaml, but it has been ported to other languages. So for example, F# and template Haskell have both versions. And the reason is that, they were introduced in multi-stage programming. The reason many languages have both flavors together is because although they offer nice static guarantees, they are limited in the sense that they cannot do code deconstruction. So here's an example. If we try to do a max function to construct a piece of code where some variables are unbound, it's not going to compile. And if it compiles, we get a code type that reflects the type of the code fragment represented by the quotation. So we can also manipulate open terms usually. So here you can see that the X is actually bound later. So we are passing the open program into a function f, and then the X that is inside that program is captured later. So it's a very nice approach. The problem is that it's purely generative. So that's what I said. You can only construct programs, and then once the program is constructed, you cannot analyze it, you cannot decompose it. Also, there has been problems with running open code and doing unsafe things with open code, but this has been addressed to some extent in recent works. So with our approach, we try to do the best of both worlds. So Squid is a library, a Scala library that stands for Scala Quoted DSL. It's the approximate contraction. It's a macro library, so it's a pure library that was implemented without modifying the Scala compiler. And it allows type-safe metaprogramming via quasiquotes. So it's actually a superset of multi-stage programming in that you can do everything you can do in multi-stage programming, but additionally you have code pattern matching, and you have some specific primitives to help with program transformation. So we're going to see recursive term rewriting, speculative closure, we'll see in a minute. So the quasiquotes ensure that metaprograms are free of runtime errors, and that includes no type mismatches and no unbound variables. So our work focuses on type-preserving rewriting of expression-based programs and handling variables in a sound way, both bound and free. with this nice quasiquote-based interface. We have in our paper description of the Scala implementation and formalization of the core language with a proof of soundness. So how does it work? The pieces of code, the code fragments in Squid have two type parameters. They are code of type and context, where type reflects the type of the program fragment and context reflects its context requirements, which is basically the set of free variables that may appear in the term. So here's a simple example, right? P is a program fragment that represents a lambda abstraction, and it has type code of int to int, and since it doesn't have any free variables, the context is empty. And we can do pattern matching on it. So here's the syntax of pattern matching, where we match, as a pattern, we match a lambda abstraction that has a different bound variable name, but it's okay. And what we do is that this n here extracts whatever is found in this position. So we're going to end up with an open code fragment with the context type referring to this free variable that has been extruded. And this evaluates to code of y times 2, where y is a free variable, and we mark this, we make this explicit by adding a question mark in front of the name. So you can also write programs with explicit free variables manually if you want, and this is how you do it. This is equivalent to the expression above. And then if you insert a term that contains free variables inside a bigger term where these variables are bound, it checks that the types are all right, and that then it constructs a program that doesn't have the free variables in its type. You can also do free variable substitution, and the syntax is the term dot the free variable name, arrow, and a program that will be put in place of every free variable. In this case, we substitute the y that we got in Q here with a program fragment equivalent to 3. So we also have the primitive for program rewriting that applies pattern matching, but on the whole program, on every sub-expression of the program. We can do things like list fusion. So here this matches a list of some arbitrary type TA with two functions, mapped to two functions, and we can rewrite it to the composition of the functions, right? This is a simple example. Now, we also have speculative rewriting, and so this means that whenever you see something that shouldn't happen during a rewriting, you can always call abort, and it will give the control back to the innermost rewrite rule, and it will just straight go to the next case. Now, this is useful in combination with free variable substitution, which is lazy, in the sense that if you try to substitute a variable in a program that doesn't have occurrences of it, you never actually evaluate the program that you pass. And if what you pass is abort, this means that if the program is, if the variable is free in the term, you abort the rewriting. If it's not, you just return term, but you remove x from the context requirement in the type. So let's look at a simple program that we may want to optimize. It's a program that takes a list and some default value, and we're going to compute the maximum of that list using fold left with an accumulator of type option of int, starting from none. And for each value x, we're going to take the maximum of what's in the accumulator if there's anything. So this fold function on the option type is equivalent to pattern matching. And then at the end, if there's no value, if this evaluates to none, what we return is the default value. So here's a more efficient imperative version. So it's really exactly the same thing, but it uses mutable references and an imperative loop. So it's actually more efficient. So it's a desirable thing to rewrite the program above to the program below. Now let's see how to go optimizing this thing. So we're going to define a function that takes a program fragment of type T in some context C, returns a program fragment of the same type. What we're going to do is a fixed point rewriting, meaning that each case will be applied over and over again until it converges. Hopefully it does. And what we do here is that we match applications of fold left on lists, and we're going to rewrite it to a mutable variable holding the current state, as well as an imperative loop. We also want to normalize a little the methods that are being used in the program to make it easier to write further transformations. For example, get_else for the option type is really equivalent to a fold, right? And we also can add some simplifications, like some value.fold can be simplified. And what's important to notice is that if you make mistakes in these transformers, you get type errors. So Squid prevents you from doing things that are that would lead to programs where variables are unbound or the types are mismatched. Now, here's the tricky part of the function. We're going to look at variables of option type, and the goal is to convert them into two different variables, because we don't want to pay for boxing, for allocating options on the heap at runtime. So what we do is we start by defining two helper values that represent just free variable references of type ref of Boolean and ref of T0. And we're going to rewrite the body. So I forgot to mention, but this pattern matches a variable that is bound to some local value, and then the whole program that occurs after this, so the body of the late binding. We're going to rewrite this body by looking at the usages that are made of R. So body.R is going to match this free variable R that we extruded from here. And so we were going to rewrite an access to the variable on which we call fold. And this we write in terms of the free variables that represent the flattened variable. Right, and we rewrite assignment in the same way, assignment to a function. And then at the end of the day, we compose the final program. So triple quotation mark, it just means it just allows you to have returns, line breaks inside in the middle. So here we bind the two free variables that we have been using and that we have introduced in the body, B2, in the rewritten body. And we insert the rewritten body at the end, where the occurrences are captured. And we're making sure here that if there's any occurrences of R left in the program, we abort the rewriting. We could also recreate an option from scratch if this happens, but it's not clear that this would be a good idea because it could lead to some programs being slower than the original one. If we forget any of these steps, if we forget to bind the free variables that we have introduced, if we forget to make sure that no R are left in the final program, then we're going to get a type error at compile time. So I'm going to just talk very quickly about the formalization. We have two contexts, the context for the current term and the context that is outside of the current quote. I'm going to skip this and just go straight to two simple rewrite rules that are essential, where you can see that if a type, if a term can be typed in some context, C and outer context gamma, then when you quote it, the context in which you typed it becomes the context of the code type of the quoted term, and the outer context becomes the inner context. So our language is multi-stage, but we only have two contexts, and this is because we do some simplification, but this is without loss of generality, so we avoid complications with context tags. I mean, this is my point. Yeah, so let's conclude. Squid offers capable type-safe metaprogramming techniques. It's an extension of multi-stage programming with pattern matching. It tracks free variables in the type system. It abstracts the name of bound variables, so the name of bound variables doesn't matter, as we saw. You can match bindings using different names. And we have some very nice primitives to make sure that rewritings are type preserving and don't introduce pre-variables. And finally, speculative rewriting based on lazy variable substitution turns out to be a very useful pattern in practice because it enables a lot of different optimizations. So this was encoded in Scala thanks to the macro and the expressive type system. And the framework is open source, can be accessed at this link. And that's it. I'm a bit early.
where you can ask questions anonymously. So it's hashtag POPL'18, we're in the water courtroom. So if you don't want to step up to the mic, we are also taking anonymous questions.
You summarize the connection of this work to other work with dependently typed programming, say in proof assistance that does manipulation of syntax trees with similar constraints?
I'd say the main difference is that you don't have to write proofs manually, right? It's all encoded in a type system, and the type system is...
But that is the kind of approach I'm talking about with dependently typed programming languages. It is, you don't have to write separate proofs, it's just in the types of syntax trees.
Yeah, but your programs are kind of like proofs, right? They're less convenient than here. I would say here we make here we leverage actually a lot of features of the Scala type system, such as structural types and type intersections in order to abstract easily over context. And so we get a lot of things for free from the Scala type system that just works out without any help from the user. For example, we get the code type of term fragments is covariant in T and contravariant in C, which means that we get some nice subsumption automatically. And so, yeah, it's just, I think, much less of a hassle to use this than a dependently typed approach.
Okay, thanks.
Could you go back to slide 6? I think that was your first real example. Yeah, so I'm trying to understand the question mark why.
Oh, so question mark just makes it explicit that y is not bound anywhere. This is to make some things easier. For example, if I go back to the previous slide, this one, here you have max, and we don't want it to be interpreted as a free variable. It's just a reference to a global defined function.
Right, so what I was curious about is when you matched against the body of the lambda.
Yes.
You said that you were going to name as n.
So n is
x times 2.
Yes, exactly.
So I can understand the question mark y there as some term that has y free in it.
Yes, so...
but then I didn't understand...
Notice that the pattern refers to the bound variable as y.
Okay.
Right? So it's important that... so the programmer who matches P doesn't know what the names of the variables that are bound in P, right?
So I guess what... Do these alpha convert at this level or only?
Yeah, it's bound variables are automatically alpha converted. You don't have to worry about it.
But even in the context.
So
is code int val y the same type as code int val x?
No, that's the point. So the name of bound variables doesn't matter. The name of free variables does matter, right?
Okay.
You have some ways of abstracting over the names of free variables also. I haven't shown them. I have a backup slide for it, but I think we can take it offline.
Thanks.
Hey, my question is, does this quasiquote work with implicit variables?
Say it again?
Implicit variables, does this quasiquote work with that? For example, you have some implicit...
implicits?
Yeah.
Yeah, sure. So I have an example with Fusion here. If you're familiar with Scala, you'll notice that the map method actually takes implicit arguments.
Okay.
And so these implicit arguments are resolved at the time the quasiquote is compiled, is type checked. And so they are there actually, but you don't see them, right? So you can totally ignore implicits. Well, at least when they are implicits that can be materialized from the without any special context.
Okay.
And so if you write this code and if you pattern match with this syntax, they are there, but you don't see them. The implicits.
Okay, thanks.
Yep.
So we actually also have one question
Mhm.
from the internet. How do you handle weakening?
So this I think I have addressed it by saying that the code types are contravariant in the context parameter, and we use Scala subtyping support with intersection types and structural types. Mm-hmm.